Hi guys, so today we'll be doing some ML stuff. Uh, so it's principal component analysis today. You must have heard about that if you have been doing a bit of ML. If not, don't worry, I'm going to explain it anyway. Yeah, interrupting. So this tutorial is basically for more of a coding approach to do PCA, not using any existing library. That is their scalar utility of PCA. But one more important thing that is there is that it's also important to understand the mathematics behind PCA. So I'll be explaining a bit of it here, and I'll be using eigenvalues and eigenvectors here. But the explanation why these eigenvalues and eigenvectors are important, right? How singular value decomposition that I'm going to mention in the later part of the video is important, right? Why, how it is working, and how it is actually doing the dimension reduction. Okay, that explanation, if you want that like a ground concept, you might go to the description part, and I have put a link to a particular video that I have found like very good, quite good for intuitional explanation. And apart from that intuitive explanation, you can go for another link that is there in the description as well. That is basically a Stack Overflow question answer link, and that link will be there because see, I'm not using a singular value decomposition here directly, but I'm using eigenvector and eigen value calculation here, and using that to do the PCA. Okay, but usually it's SVD concept, SVD for singular value decomposition. So that content will tell you how SVD and eigenvector and eigenvalue calculation in this context will be almost the same. They will give you the same result. So please go to that link once you are done with this video. If you feel like you want more concept on this particular PCA thing from a mathematical point of view, I think you should visit that link. I'm sorry. Please continue. So let's come to the problem straight away. Okay, because whenever you discuss any kind of ML tool, it's more convenient to explain that problem that it solves usually, so that you can be a more solution oriented and be more focused towards the solution that particular tool serves. So today's topic is PCA, that is principal component analysis, and what it does. Okay, so let's think of a data set which has two features. Okay, so two features, maybe a flower, and two features of the flower, maybe the size and the color of the flower. Okay, and say the color is being in white, like black and white. That's why the color can be represented as a continuous value, and the size being the diameter of the flower. Okay, so say we have 100 data points. That means we have 100 flowers with us, and each of the flowers have two entries, that is the size and color of the flower, and the color is like black and white color. Okay, so it's easy to visualize it. Why? Because you take the data, and once you have got the data with you, you can actually plot it. So say you are using a XY axis, and along Y axis you are plotting the size of the flower, and along X axis you are plotting the color of the flower. So once you plot it, if the samples were taken from say three classes of flowers, maybe three types of flowers, so what happens is that you will be able to clusterize, like visually cluster the data points. What I'm trying to say is that say you're taking three kinds of flowers, say flower 1, flower 2, flower 3, which is type of the flower, not the exact instance. So maybe marigolds, sunflower, and daffodils. Okay, so these of mostly you will be having different color or size for each of the kind of the flowers, and once you plot it, you will be seeing, okay, maybe one daffodil is not exactly similar to the other daffodil, but it is kind of near, like closer than the other class of flowers. Okay, so you'll be able to visually cluster three spots in your 2D graph. 2D because xy. Okay, so well, cool, that's not the problem. Actually, that is not the problem. So what is the problem? In real world you don't get only two features. Okay, and we, like in human mind, we can go up to at most 3D. You can visualize 2D in a screen, but you can extend it up to 3D with your understanding. But usually in real world, data can be like hundred of dimensions, and it becomes very difficult to visualize them. And because you can't visualize, you can't visually cluster them also. And usually this kind of analysis are needed before you go for applying some machine learning algorithm on the data, because you need to know how the data is actually. You need to analyze the data so that you can select the particular algorithm or whatever you're trying to apply on it. Okay, so what's the way out? There are multiple ways to deal with this, but the branch that deals with this is basically called dimensionality reduction. Okay, that is a solution. And what is the problem called? The problem is basically feature extraction. Well, it can also be termed as feature selection. So combinedly we can say it is feature selection and extraction. So what is feature selection? Maybe say you have 100 features and all of them are not useful. Okay, so what to do? What you can do is basically you can eliminate few of them. So maybe you are selecting 50 features out of them, and you are going on with the rest of the 50. Okay, this part is called feature selection, but that is not what we are going to deal with today. We are going to deal with feature extraction. So what I mean by feature extraction is that, say you have 50% of the data. So basically it's somewhat like this, that the data is hidden inside these features. Okay, and you need to extract it. So when I say that I am visually clustering this data, that means this x and y axis, that was in case of my flower classification, 2D classification, we had size and color, and the data that was helping me to like differentiate between the different kind of flowers was basically hidden into these two dimensions, xy. And so will be for any other classification problem, that the feature that is the distinctive feature, you can say, is hidden between all the features. Okay, it's kind of distributed between all the features. So the point is that you need to extract the feature. Maybe there are x, y, z, three axes, okay, in some other problem, and there is 33% data inside the x axis, there is 33% data in y axis, and 33% data in z axis. Okay, so you need to extract it out and compress it into fewer dimensions. So maybe in this case you were using 3 dimensions, you want to compress it to 2 dimensions. Okay, so you want to compress and minimize the, because see, when you are in case of feature selection, you are totally eliminating 50 features out of 100, and it's not that all the features are like all of the features have zero contribution. Maybe their contribution is very minimal. Okay, now what you want to do is that you want to minimize the number of dimensions as well, want to minimize the loss due to eliminating dimensions. Okay, you don't want to simply like eliminate all the dimensions, all the 50 dimensions, and keep 50 dimensions, because in that case you are going to lose all the features, all the data that was there in the 50 eliminated dimensions. So the way out is the way out can be actually different algorithms. One is PCA and the other is LDA. So LDA is a supervised algorithm and PCA is the unsupervised one. So in case of PCA, as I said, the distinctive feature, the feature that differentiates the one from another. So in case of PCA, we take the term variance. Okay, how much difference? So you can think of somewhat like this, that say there is a XY plot, okay, and the data is somewhat spread along x is equal to y line, okay. So the data points actually, okay, so maybe this is a XY plot, okay, and you are putting the data, and it seems like you can fit the data in a one line, and that particular line is say x is equal to y. That means x and y both have a variance of 50%, like both have a 50% contribution towards the distinctive features. In case of LD, it's quite different. It depends on the classes or the labels that you have given it, and that's why it is supervised learning. And in case of PCA, there is no labels given, okay. So what happens in PCA is that we use the variances and try to compress the number of dimensions. Okay, now I'm going to actually, so this was kind of an overview kind of thing, and we'll go straight dive into the code and understanding the maths behind it. Let's go. Okay, so let's import NumPy first. I think that's what we need. Okay, let's have another, like a data set. Say that is sklearn.datasets, import, let's use iris, load iris, because we have been talking of flowers. So let's take the x value only, because we are not going to use labels because PCA is unsupervised. So the x will be load iris data. Okay, cool. So what is x? Let's see. So x is basically data. Now see, let's discuss this data. Okay, this is basically the iris, the famous iris data set, and it was kind of engineered or maybe like created for benchmarked classification problem. Okay, so whenever you devise a classification problem, it's better to go with this particular iris data set. Okay, it's quite often used for benchmarking tests. Okay, so how the dataset is basically, it's somewhat like this, that this is a 2D data set, and each of the row, that is this particular that I've highlighted, so that is giving me 4 features of the flowers. Okay, what are the features of the flowers? Let's see. Load iris, I think. Yeah, the feature names, right? So copy, yeah, see, these are the features. Okay, there are sepal length, there are sepal width, petal length, and petal width, and I think there are 4 kinds of flowers. Let's check it out. For that we might need to, yeah, there is 0, 1 and 2, basically 3 classes, that is setosa, versicolor, and virginica. Okay, these are the 3 kinds of flowers that we have, but that is not the problem. That is kind of off topic here because we don't need labels, but that is for your general information. So here we have each of the rows are having the sepal length, sepal width, petal length, petal width. So these 4 features. Now we are going to compress it. Okay, and each of the rows, like one row is for one flower and the other row is for another flower, and we don't have the labels currently for this algorithm. Okay, now let's understand what we have to do after this. So what we need to do is first is that, so let's understand what is PCA. Okay, what we do in PCA actually. So in case of PCA, so PCA is basically a transformation kind of thing. What it does is that you have to understand, so if you know Euclidean system, we have x, y, and z. So usually if it is a 3D Euclidean system, then we have XYZ axis. Okay, if you have higher dimensions, say for general n dimensions, then you can have the axis like x1, x2, x3 up to xn. Okay, but the catch here is that each of the axes is like perpendicular to the other one. Okay, that is the catch. So what we do in PCA is basically we try to rotate and shift the coordinate system. Okay, that means the relative property between the coordinates is conserved, but we want to maximize the variance because we are going to we are going to reduce the dimension. So for more clarity, you can think of somewhat like this. So we have a XYZ coordinate system, and you are kind of shifting it and rotating it. Okay, now after shifting and rotating, you are left with say x dash, y dash and z dash axis. Okay, after all the transformations, now you're going to select only x dash and y dash. Okay, so you're going to leave the z dash totally. Okay, so you need to make sure that the variance property, the variance actually, which is a property of like statistical property of the data, needs to be sorted in decreasing order, so that the most of the variance is there in the x-axis, and then in the y-axis, and then in the z-axis, so that when you are leaving z dash, you are losing a minimal variance property. Okay, so that is our goal actually. We want to reduce our dimensions, but we want to minimize the loss of data. Okay, so how we are going to transform our coordinates? Basically, this is a problem where we transform our coordinates, but how are you going to do that? So of course it's a transformation matrix. So you get a data and you multiply it with a transformation matrix and get the transformed data. Okay, now so here we have n is equal to 4 dimensions, right? But we want to compress the data to 2 dimensions. So that is the variable, that is nPCA is equal to 2. Okay, clear, right? 4 dimensions, you are going to compress it to 2 dimensions. How? Okay, as I said, we need to have a transformation matrix. So the whole problem now is to get the transformation matrix and multiply it. Done. That's all. Okay, that's it. Nothing more. So, but how are you going to get that? So what I'm going to do is that the first part, so this is an important part. Okay, let's get another cell. So let's name it maths part. Okay, because this is where, so this was normal coding part, we loaded all the stuff and all. Now we are going to do the important steps here. Try to understand. So I have a X, that is a matrix, that is basically a NumPy array, but a matrix because it is 2D array. So what we're going to do is that we are going to transform Rx. How? X dot mean axis is equal to 0. What I just did was, see, this was my data, right? So I had 4 columns in my data, and so this x mean axis is equal to 0 is giving me, so what, let's see what it is actually. See, there are 4 values. Okay, so it's a column wise mean. So mean for first column is this one, then the second column is this one, and so on. And so I am basically subtracting this particular value with each entry in the first column, also subtracting this particular value from each entry in the second column, that is this second column. Okay, so it's about finding the column wise mean and subtracting the column wise mean from the corresponding column, because you have 4 columns. in this data and in this mean also. Okay, now that is what transformed x, you can say. That's why it is transform x, trans x. Okay, so what after that? Now the problem is basically, the problem comes here to finding the eigenvalues. Okay, now let's find out the eigenvalues first and then we'll see what they are actually. So values comma vectors is equal to np dot line algorithm. I think it is Eigen trans. Okay, wait. This is not trans. Okay. Before this, we need to find out the covariance of the data points. Okay. So C is equal to NP covariance of x, because x, the covariance for x and trans x is going to be the same. You can validate that because all I'm doing is subtracting the mean. Okay, but that has nothing to do with the variance. Now what is covariance matrix? So this is giving me the covariance matrix actually. Yeah, C. Now you can see what C is basically. The shape of C should be 4 cross 4. Okay, I think some problem here. It should be transformed. Yeah. See, so what C is basically here is that it's a 4 cross 4 matrix. So you must be knowing variance and covariance. Okay, you can just Google. It's a simple statistics thing. So what happens is that it's a matrix. So you have 4 features. So 4 cross 4 matrix. So the first entry, that is 1, 1 entry, gives the covariance of feature 1 and feature 1. Now covariance of the same thing is basically the variance of that thing. So the 1, 1 entry is basically the variance of feature 1. The entry 2, 2 is the variance of 2. And so it is the same for the diagonal. Every entry in the diagonal. But what about the non-diagonal entry? So for the non-diagonal entry, say 1, 2, that entry will be basically denoting the covariance of feature 1 and feature 2. Now come to 2, 1. So 1, 2 was covariance between feature 1 and feature 2. So 2, 1 will be the covariance of feature 2 and feature 1. But both are the same thing. That's why this matrix is basically symmetric matrix, right? So this particular C is giving me the covariance matrix of the data. And that matrix, if you want to tell me the significance, it kind of gives the variance and covariance between the different axes. It also can give you a correlation between them. Okay. So yeah, now we are going to find out the eigenvalues and eigenvectors for this C matrix. Okay. Cool. What are the values? Okay. Now we need to focus. Okay. That is this is the most important part of this tutorial. So you have got values and vectors. So let's see what are the values are. Vectors. Okay. Now what is happening here is that we have some values and we have some vectors. Okay. Now think of these vectors. Think that these vectors and values are interrelated. Okay. Now these values, if you sum it up, it will give you the total variance of the data point. It will give you the total variance of the data point. How much variance is there? Now see, although it is sorted in decreasing order, it is usually not. Okay, but that is not the point. The point is that these values and the vectors are interrelated. How? So focus on the vector. Look at the vectors. Okay, so we have a vectors and that is having a shape of 4, 4. Okay, so say vector. So I was talking about shifting and rotating the axis, right? So you are rotating x axis to x dash. Now if you think of this problem as 4-dimension problem as w, x, y, z. Then let's consider we have transformed the whole thing into w dash, x dash, y dash and z dash. The first column, not the row, okay, the first column can be, so I can't select the first column actually, I think, okay, I can't, okay, but you can see here I have highlighted them in sequential order. That particular first column is basically giving me the w dash, okay. W was already there in the what do you say, the original data point. W was basically the x-axis, nothing else, okay. So but the new w can be represented by this particular 4 values, okay. So how do we use that? Okay, so I was also talking about the values are interrelated with the vectors. So w dash is having an importance, so is x dash and y dash and z dash. Now if you see the values, the first entry in the values is 4,22, which is the highest in the matrix, which is the highest in the values array. So that means that this particular column that I said was w dash is having an importance of 4,22, which is the highest. So if you like leave all other axes like y dash, x dash, y dash and z dash, you are still left with a huge importance, like huge variance, okay. So compressing this piece, like this particular data point to one axis, is you are also like you are kind of left with a huge variance. You're not losing a lot of data, but in this case we are only like focusing on keeping 2 data points only, like 2 dimensions only, not 1. So what we're going to do is that we are going to get our transformation matrix. So transformation matrix is equal to vectors. Now see, we need to select the columns, okay. I think I missed something here. See, as I said that the values are kind of kept in decreasing order, but it won't be the same as in other problems. So you need to actually keep a method to sort them. So how do you sort it? Arc sort priorities. So say these are my priorities. Priorities are kind of denoting the importance values. Yeah. Now arc sort is by default in increasing order, but we need decreasing order, right? So this is a like shortcut to reverse any numpy array. Cool. These are the priorities. Now see, the priorities will be so as it goes. The most important is the 0th axis, that is this column, okay, this column. The second important is the second matrix, second column. The third importance goes to the third one, and so forth, fourth one, okay. Now transmatrix. So what is the transformation matrix then? So we need to select the the columns with the more priorities, right? So in my case we have NPCs, right? So we are going to select those columns, say the first 2 columns basically, right? The first 2 columns will be vectors, so priorities, because priorities is giving me the decreasing order, and then only keep the first NPCs. NPCA is equal to 2. That is the transformation matrix. We don't have NPCA. Okay. Now what is transmatrix? Let's see. Yeah, this is the transmatrix. Now see, I have only 2 columns. So the first 2 columns actually. Now we need to use this transformation matrix to transform the data. That's all. Okay. So we had our trans x, right? Trans x, and this transformation matrix, right? np.matmul. This is basically a matrix multiplication function which will give me something. Okay, so this is the like transformation result. Now you can see one thing, you can check if it is right or not. So for that I'm going to import the actual PCA algorithm that is there in the sklearn. Decomposition, import PCA. Okay, so PCA 2, because we are going to compress it to 2, and the original data was x, so fit transform x. See, 2.68 minus 2.68, it's almost the same, right? One more thing left. So we have reduced our dimensions, right? But like, okay, that's fine. But how much data or how much importance have we lost in this case? That we can do. So basically these values, those are eigenvalues. Okay, so you can think of it somewhat like this, that we have selected the first two, like the highest two values in the values. So we have lost these two actually. So a clever way to find out how much variance we have or we have been able to like retain can be written in this expression, that is values priorities, because it is sorted, and then the first two priorities, right? Sum divided by so 97% variance has been retained. So that was what basically this PCA was. One more important thing, that is one more catch here. So actually this was you can say sufficient mathematics that I told here, but it was not sufficient, but it was sufficient to help you code out the whole thing in Python. But to actually understand why this is happening, you need to go through singular value decomposition. I'm not going to cover that part in this tutorial, but the point is that these vectors here are orthogonal. As I said, this x, y, z axes are perpendicular to each other. Also, these four vectors, as I said, these four axes, because each of the columns are one axis, these columns are orthogonal to each other, and each of the columns are having a weight of this like as explained in this values part, the values array. Now you can say why, and again I said I'm not going to cover that part in this tutorial. You have to go through singular value decomposition in like you can Google it, you can get it anywhere. Once you understand that, you will be understanding the whole thing in PCA. But like if we don't build up from SVD, like from the ground, you can, if you believe me that this part is, as I'm saying, that it is giving you the importance of the variance, then the rest part is quite intuitive. It's not a big deal. So what you do is basically you subtract the column-wise mean, you find the covariance matrix, you find the values and vectors, and then you sort, like you select the first two or three values, the first two or three vectors depending on the values, like highest values, and then use the transformation matrix to transform the x-axis, like x data, that is the capital X, that was the matrix here. So you use that, you do a matrix multiplication and get the transformed matrix. Okay, so thank you. I think this was a bit tedious stuff. if you guys have any kind of question, you can put it in the comment. And I'll like appreciate if you guys go and Google singular value decomposition and understand that part. I think it is more intuitive if you try to attack that part from a mathematics point of view than a computer science topic. Thank you. So this was PCA, coding PCA from scratch in Python. So if you guys liked like watching this video, please hit like and subscribe to my channel for more updates and for more similar videos. You can also put in comment what topic I can make my next video on. And if you have any question, please put in the comment section, because I think this PCA was more of a conceptual thing, and maybe I wasn't able to put everything in a very crystal clear manner, but I tried from my point. Will appreciate if you guys comment. Thank you. Bye.